Okay. Right, so I'm now beginning my lecture, which I labeled lecture on the 8th of January 8-1-17. So I'm just doing it shortly after the one I did labeled 7-1-17. So we're just continuing what we started with in terms of the sinusoidal and periodic functions, and I finished with the sinusoidal functions, and now I'm looking at a more general periodic function, namely the tangent function. So I just described that on the board. And by the way, these evaluations they're different if I approach from above. So if I approach from above, that's pi over 2 positive, and that's going to be going to plus infinity. Sorry, minus infinity here. So it's different from this one, right? So that's when I approach. That's when I approach from above. Okay, so you can see that this is a periodic function. The period here is pi rather than 2 pi. Okay, so now just generalizing this to these values here. We have y is equal to, let's try a different color, slightly different color here. So this is y, it's the same color, sorry. Okay, it's a different pen. Okay, so the general function in this case would be shifted and stretched and, well, shifted both in the vertical and horizontal directions, and stretched also in vertical and horizontal directions. So it has an A, B, and a C, and a D. All right, so the book gives you more information on this, but here A is not an amplitude. A is a stretch function, is a stretch factor. Stretch or shrink factor. So there's no amplitude because there's no maximum value for the function. It goes all the way off to infinity or to minus infinity. But the stretch factor will indicate where the function goes through when you go through a quarter period, which is here pi over 4. So quarter period would take you to 1 for the tangent function. Here it would take you to the value a. Okay. So erase this here. Okay. And b, the period now will be pi over b, absolute value of b. And we'll also get a shift. The book calls it a phase shift, but I might prefer to call it a shift in x, or an x shift, which is c over b. Okay, so that would be just where, for example, instead of the function starting at 0, at x equals 0, instead of the y value being 0 here, it might start being 0 when x is 3 pi over 8 or something, let's say. And then, so it's shifted over here, and everything will be shifted over there. And that will be the x shift c over b. Okay, so b is a stretching or shrinking in the horizontal direction. This is in the vertical direction for A, and then this is the horizontal direction for B. And C can be thought of as or C over B can be thought of as the shift in the horizontal direction, or the x direction. And D is a shift in the vertical direction, or the y direction. Okay, so that's the general case. I'll let you look at the book to see examples of that. And the book also goes through examples such as for the secant function, and for the cosecant function, and also the cotangent function, and how to sketch them. But I'm afraid I'll have to skip those in order to just move on. But okay, so the next part of this chapter then is it has to do with the inverse trigonometric functions. Okay, if necessary, I might go back to this to do some examples. So in some review section, I might have to do an extra lecture, but in a review session, perhaps I'll do some extra problems dealing with the tangent function as well as the sine and cosine functions. All right. Okay, so in this section, inverse trig functions, inverse Okay, so for the inverse trigonometric functions, we remember that what the sine and the cosine functions look like. Okay. Actually, let's start with an example. So if we know the value of sine over pi over 6, we can now calculate that, and that value is 1/2. So if we look at a value if we're given an angle or a number in radians, then we can take the sine of that real number. In this case, it's pi over 6, and we'll get a value 1/2. So we know how to do that by the unit circle definition. This is 30 degrees. All right, so there's also get a right angle triangle, 2, 1, and root 3. That's 30 degrees. And so it's 1/2. Okay, if you want to do it using the standard special angle triangle formula or picture. All right, so now the question is, what if you had the value of the sine function? You're given a value, it might not necessarily be 1/2. Then how do you find the angle which will give you that? So let's say we're given 3/4. Why not? Okay, so that could be a value for the sine of x for some angle. So you'll have a triangle which looks like this. It's going to have to be a bigger angle, let's say 3, 4. It's not a 3, 4, 5 triangle, but this will be 16 minus 9, which is root 7 over just root 7. Okay, so what angle is this? Well, the answer would be, if we knew the inverse sine function, it would just take the inverse sine of this value, plug that into our box, and then it will give us the output x. All right, so the inverse function always undoes what the original function does. We start with x, we get the value 3/4. In this case, we'll just plug in the value 3/4 and get back x. But remember, the requirement for a function to have an inverse is that the function should be 1-to-1. What does a function look like? It's not, if we draw it like this, its full domain, over all the values for which it's defined, for all the x values, then the domain is all real numbers. So we saw that before. But if we do a horizontal line test, if we draw a horizontal line here, then that intersects the graph in many points, infinitely many points. Okay? So this is not one-to-one. I'll put a dash there. Not, or just put in the 2. Not one-to-one. But let's see. How can we make it one-to-one? Well, remember the way to make it one-to-one is to restrict the domain over an interval where the function is either completely increasing or totally always increasing or always decreasing over that interval. So a natural interval to take would just be, say, from this value of x to this value of x. So this value of x is minus pi over 2, and this value of x is pi over 2. We could also take the interval to be from pi over 2 to 3 pi over 2, which is over here, which will give us values from 1 down to minus 1. However, that would lead to a different definition of the inverse function. So remember how things would change there. It's not too hard to figure out what that function is, but there's this standard definition that we'll abide by, that we'll go with, which is also the textbook's standard definition, and it's also what the calculators use as a standard definition. So basically, if we want to make sense of what the calculator is telling us, then we should stick with this definition, not go somewhere else. That'll just make it easier for us. All right, so here's my x for the sine of x, right? This is the sine of x. Y is equal to the sine of x here. I'll just label the axes. So I want to restrict from x between minus pi over 2 to plus pi over 2. All right. So this is what it looks like. It's just this piece of the sine function. Now we simply want to take the inverse of this function. And we'll define the inverse sine then to be the inverse of this part. Okay, so here the domain is minus pi over 2 to plus pi over 2. It's a restricted domain. Restricted so that the function is one-to-one on this interval. It passes a horizontal line test. The range then is all the values from minus 1 to plus 1. This is minus 1 here and plus 1 here. So the graph of the inverse function, y equals sine of x, will have, this is true for this function, so the domain and range are switched around for the inverse function. Domain is now minus 1 to 1. The range is now minus pi over 2 to plus pi over 2. And the graph, remember how to get the graph, you take the line x equals y equals x, which actually will be this line here. It'll be just tangent to the sine function as it goes through the origin. It's just the scales are a little bit different. This value is about 1.5, by the way, 1.57. So this is going to be 1 around here. It's a little bit shrunk in, so it doesn't look too good. So let me just draw this again. I think the book does this part well. So this is 1.5, or pi over 2. Right around pi over 2 here. Here's the value 1. So instead of going directly up like this, that's the line y equals x. it goes like this. If you look at a calculator, all right, and you put in the values sine, very small values, let's say sine of 0.001, then you get, this has to be in radians, then you get the same value. So no matter what number you put in here, as long as it's small, it's very, very, very close. It's not exactly the same, but it's very close to this number. It's always less than the number itself. Actually, that's true for any value of x, any real number. It's always less than or equal to x itself. Okay, because the graph lies always. Oh, actually, this is for x greater than 0. Oh, yeah. For x less than 0, it's the other way around. Because you have to change the sign of both sides. That also changes the sign of the direction of the inequality. Changes the direction of the inequality. Okay, so here if you flip this about this line, it will be going like this rather. Here the slope goes to 0 at the top of the peak. It continues on like this. Here the slope goes to plus infinity as you go to this point. But it's not, the function itself is not infinite there, it's finite, and is equal to pi over 2 at that final endpoint. It's just the slope which goes off to infinity. Whereas on this side, you go all the way to -1, and the value of the function goes to minus pi over 2. So this is the function y equals sine inverse of x. Now here I'm going to make things clear by writing in the brackets or the parentheses to make it a bit clearer. So actually normally I'll not write down the parentheses, but if there's any issue with interpreting what I'm taking inverse sine of, I'll put the brackets in. If there's any possible ambiguity. Okay, so this line is a line of reflection from the previous graph. It's good to draw both in at the same time, so let's just do that. So the previous would be, say, in green, and the previous is the original sine function. Okay, and it goes like this. So this point gets reflected to this point gets reflected to this point. It just gets reflected about this 45-degree line. Okay. To get the inverse function. That's always how you find the inverse function by graphing. You just flip it over this line, which is y equals x. All right, so let's erase this. It's not too important for us right now. So let's look at the next inverse trigonometric function. That's the first one. The next one is to find the inverse cosine. I'll look at the graph of the cosine graph, the graph of the cosine function. Now that starts off at 0. It's y equals 1. X equals 0, it's y equals 1. And at x equals pi over 2, that's where it goes to 0. And at x equals pi, it goes to -1. All right, now the crucial thing is if I go in this direction to the left of values which are of x equals 0, so to negative values of x, then I'll start to go down, and that will, if I include that part of the graph, it will give me a failure of the horizontal line test. So if I take this interval is nice because it includes all the possible values from -1 all the way to +1 for y. But if I go anywhere beyond these endpoints, then I will repeat values of y, which makes it not a one-to-one function anymore. So I can't take the inverse of that. So and I want to choose a restriction which is nice. If I can't choose the same restriction as I did before, notice, because that would be from -pi/2 to +pi/2, and that part of the cosine function already fails the vertical line test. So plus I'm not including all possible values from -1 to 1. For the sine function, it does work because of the shape of the sine function in that interval. It does go from -1 to 1, and it doesn't repeat itself. It's completely increasing in that interval. Here, it's completely decreasing in this interval, a new interval. So we'll restrict to that interval and make it 0 to pi as a domain. That's our new domain. Then the range is also -1 to 1, -1 to +1. And now here's what the inverse function looks like, just by, again, flipping over the line y equals x. Okay, so I'll draw a little bit smaller in here. This is 1, this is pi/2 is somewhere here. Pi/3 is up here, or 3 is up here, so pi will be up here. This is pi/2 here. Okay, so it looks like this. It starts up at -1 here, it goes backwards to -1. Right, so as I go from here, this point gets flipped over the x equals y line, which is over here. I drew that in red before, so why not use my red pen? So that's the reflection line about which I reflect things. And so the new function will be, the old function starts at, this is 1, starts at 1 and it goes down to 0 at pi/2, and then it goes to -1 at pi. So 1 is less than that, so if I draw the inverse function, then it's just this point gets reflected to this one, this point gets reflected to this one, this point gets reflected all the way up there. Okay, so I hope you can see that this blue thing is a reflection of this green thing through that red line. Okay, so, and then labeling this, then I can label both axes, x and y. So y is equal to cosine inverse of x is the one in blue here. The green one is the original, y is equal to cosine x. I'll just label it here, y is equal to sine x. That was for the old graph. So let's just put it closer so we have a good shot of this. Okay, so that's what it looks like. All right, so now when we want to find the inverse sine, this, by the way, is also called the arc sine of x, and this is called The inverse cosine is called the arc cosine of x. Okay, so now remember the properties of the arc sine and arc cosine are that if you take a value in the domain of the starting function, and then you compose with the inverse of that starting function, then you get back the original value of x. Start with, I take the sine of x, and then I take this inverse sine of that, and that will give me x. As long, okay, there's one condition though, x has to be in this, x has to be in the domain of the sine of x. So it has to be between minus pi over 2 and plus pi over 2 in order for this identity to hold. If it's not in this range, if it's not in this domain, or in this interval, then I won't get back, I'll take the sine of that, I can do that, and I can take the inverse sine of that, that's fine as well, but what I'll get in the end is not equal to this original x. What I get in the end will have to be in the range of the inverse sine. We know the range of the inverse sine is that interval. So it will have to be in this, the output will have to be in this interval here. But the input doesn't have to be. So you have to be careful when you evaluate these, the combination of function and the inverse function. If however, you do it, if you take the sine of the inverse sine, well, as long as x is in this restricted interval, so that's the domain of this function now. The inverse function has sine of x has its domain minus 1 to 1. As long as x is in that range, then what you get as output will be an angle such that when you take the sine of that angle, you get back the original function. So this will always be true. But keep in mind that if it's outside this range, then this is not even a defined function. The sine inverse is not even defined outside that interval at all. In this case, this function is defined outside this starting interval, so it's different there. You could possibly choose other values, and then you won't get the final result here. But here, the only way it does make sense at all, if anything, is by choosing the x in that interval, and then you do get this identity. Hope you see that. Okay, and then same sort of thing for the cosine and the inverse cosine. If you take the inverse cosine of the cosine of x, x has to be in the range from 0 to, or the interval from 0 to 2 pi in order to get this identity to hold. And if you go the other way, it will always hold as long as x is in this domain of the inverse cosine. Oh, sorry, yeah, that's correct. So it's the same. Notice the domain is the same as for the inverse sine, but the range is different. It's now 0 to pi. So it's just the opposite. It's just the interchange of those two for the cosine function. Okay, so the third case would be the tangent and the inverse tangent functions. Okay, so here's pi over 2 minus pi over 2. Here's my 1. I'm trying to draw this to scale. And minus 1. Here's x, here's y. Here are my asymptotes. Okay, so we just draw this earlier. Actually, the previous lecture. And this graph will go through 1 at pi over 4. And then keep on going off to infinity here. And this will go through minus 1 at minus pi over 4. And go up to minus infinity here. Now remember that this function repeats itself. So if we start with this part of the function, then we get through all values of y just by choosing x appropriately between minus pi over 2 and pi over 2. You see, we'll get all the possible values of y, which are the real numbers, all the real numbers. So d is now restricted to be between, and not including, minus pi over 2 and pi over 2. So I notice I use now the curved brackets. They mean not including the endpoints shown. Right? And the range is all real numbers, so minus infinity to plus infinity. Now if I go any further, I will start repeating, and that will give me a not one-to-one function. I'll lose my one-to-one property. And the function will always be increasing, but it will repeat itself, so I can draw a horizontal line and get two values of x for the same value of y. Okay, and I don't want the 2 for 1 deal in that case. All right, so I just want one value of y for each value, or one value of x for each value of y. Then I can take the inverse function. Now what does the inverse function look like? Okay, well this graph is, I show the line y equals x, or x equals y. That will pass right through like this. So this is 1 here. This is 1, let's say, here, minus 1 here. So this is a line y equals x. So it's this line I reflect through. And when I reflect through it, I get, well, now I'm changing for my color, my color scheme here. I'm trying the green now as a new function. So the green will look like this. It will go towards this. Now this now becomes a horizontal asymptote at 1. I'm sorry, pi over 2. It's a little bit higher. So this graph will go like this. For positive x and for negative x, it goes through minus pi over 2. It goes to the horizontal asymptote at minus pi over 2. Okay, so now in this case we have, that defines for us the inverse tangent of x. So it's really like this, or also called the arctan of x. May not have the parentheses there. All right, so again, it undoes the operation of what the tangent does. The tangent takes a real number x and gives you the output tangent of x. And in this case, we're going in the opposite direction. We're given the value of the output of the tangent function. We want to find the input value to the tangent function. Okay, so in this case, now it's helpful to think of the trig functions more generally here. These functions f I'll label the trig functions, not their inverses. And it's good to realize what you're doing here. You're putting in, the input is usually considered to be an angle. And the output is a real number. Or ratio. They both have no dimensions. They're both unitless physically. But usually when you put an angle into the sine or cosine function, the angle is in radians. And the output is then a real number or some ratio. The inverse functions take you the other way and get you from a real number or a ratio and I'll label them F inverse and give you back an angle. So if you're given an equation, you're asked to solve for an angle, and you're just given, say, the sides of a triangle, then you take ratio of the sides of the triangle. You put that into an inverse trig function and using a calculator, and out comes an angle for you. And that's usually, if you know you have to find an angle, that usually signifies that you want to use an inverse trig function to find that angle. Okay, and we did a problem like this before where I had to solve a triangle, and we were given two sides of it, and we used that ratio to find, the tangent of the angle. I believe I did that for this 3, 4, 5 triangle. Right, and that tangent of phi was equal to 3 over 4. And then I said, well, we don't know, we can't see what the angle is, right? We can't calculate it by hand, we need a calculator. So I used a calculator and I just plugged in, I just put the tan on the other side, made it the inverse tan, acting on 3 over 4. So that's by definition of the inverse tan function. And then I calculated that to be 36.9 or something. I forget what it was, I think 36.9 degrees. And in terms of radian, it was, I guess, pi over 4, pi over 5, about 0.2 pi. Okay, so you can always check this by plugging it into the original equation. So take the tangent of this angle and see if you get back 3 over 4, which would be about 0.75. Okay, I can do that right now, just to verify that what I've done is correct. So I take the tangent of this angle and I get about 0.73 or something. So it's pretty close. Okay, so that's the idea of when to use it, be alert to when you need to use an inverse trig function as opposed to a regular trigonometric function. Okay, so back to the inverse tangent function. You can see now that all the possible values that you get, so you can, the domain of this function is equal to the range of the original function. So the domain is any real number now. You don't have to restrict the domain here. It's all the real numbers. And the output, the range though, is from minus pi over 2 to plus pi over 2, not including the endpoints, as is shown here. So it's just the same as the domain of the original restricted tan function. Okay. All right, so I've shown the graphs of these inverse trig functions, and let's look at the so-called spectral angles. So now let's look at evaluations of the inverse trigonometric functions. Spectral angles are these angles that we considered which are nice, which are multiples of 1/12 of the way around the circle or 1/8 of the way around the circle. So the spectral angles will be pi over 6, pi over 3, or pi over 4, pi over 3, and so on. So these are called the spectral angles. All right. Okay, so if we take the inverse sine of 1/2, the arc sine of 1/2, what is that? Okay, so one way to do this is, let's call this value of x. It's an unknown value. Then let's write this in terms of the original function sine. All right, so just like there's, when you write an exponential equation, there's also the logarithmic form. And if there's a logarithmic form, there's also an exponential form. You can go back and forth. This is the same thing. We can go back in terms of the expression in terms of the sine function. So we just put the sine function on the other side, leave the 1/2 there, or alternatively just replace interchange x and 1/2 at the same time as you change from the inverse function to the original function. Okay, so now this gives us an equation that we need to solve to find a value of x. Now the actual solution that we want has to be in this restricted range here. So the range, remember, is from minus pi over 2 to pi over 2. That's the range of the sine function. So this value of x has to be in that final range. So we can't just find any value of x which makes this equation true. We have to find a value of x in this range. So what value should I put in? Okay, so one value would be pi over 6. So if you remember the way if you look at the circle, unit circle, you go at pi over 6, and that gives you a value of y, which is 1/2. So that will work, and that's in this range. So it works. Does any other value work? Well, if you go a little higher, you can get this angle here, which is 5 pi over 6. 5 pi 6 also satisfies this equation. If you plug it in, sine x equals 1/2, but what's different here is that this value of x is not in the domain. It's this range here, sorry. The range is from minus pi over 2 to plus pi over 2, which is this sector of angles here. X is not in that domain, or that interval. So we don't include that. Neither is any other x outside other than this one here. So this is the only one in this interval, and so that's the answer. That's the answer to this original question. So we can just write inverse sine of 1/2 equals pi over 6. So because we know that the sine function is a function, there's only one value that's going to be the output. If we find the value with the right restriction, then that's it. We don't have to worry about looking for any other values. That's going to be the answer. Okay. Unless when you check, that's always a good idea. You can try to check another answer, and it should not work. Once you find one which does work, that should exhaust all the solutions. Okay, let me erase this. So I expect you to please look through the examples and look through the calculated ones. I might not do them all, but in this case I will try to show you better how it works. Okay, so So that was part A of a problem, one of the try problems, I believe, or maybe an example problem. B, sine inverse of minus root 2 over 2. Again, the input for the inverse trig functions is going to be some real number or ratio. For the spectral angles, it'll be some combination of it'll be a rational number times a square root of a rational number in general. Well, I mean, just for the spectral angles. But for in general, it could be any real number, positive or negative. And it should be in this domain of this is minus 1 to 1. And it is, because this is less than 1 in absolute value. And so what we do is recognize what value of x gives us minus root 2 over 2. This is going to be it's going to be an angle which this reference angle is just 45 degrees, because we know that the sine of 45, or I mean pi over 4, sine of pi over 4 is root 2 over 2. Okay, but this is a negative sign here, so where should that be? And the answer is it's going to be negative the pi over 4, since that's in the required range of values that we're allowed to get out of this function. So the output values must be in this range. Okay, so that does it for us. Remember, this is an odd function, so the sine of minus 4 minus pi over 4, I'll put brackets there, is minus 1 over root 2, or minus root 2 over 2, same thing. Okay, so that's the answer. It's the only allowed value in that range. Okay, cosine inverse of minus root 3 over 2. Okay, so if you can remember all the special the trigonometric values, function values for these spectral angles, then it makes it a lot easier. But in this case, I'll just write it out. Cosine of x, okay, call this x. Cosine of x then is minus root 3 over 2. What value of x gives you a cosine of minus root 3 over 2? And think about it, remember it's pi over 6. That's for the reference angle. So let's call this a reference angle of x. All right, and so that means it's one of these possible angles. Pi over 6 is here. This also has pi over 6 as a reference angle. This is pi over 6. This is pi over 6. Remember, there's a symmetry here. If you draw the lines connecting these 4 points, you get a rectangle. These sides are parallel to the axes. Now, which value do we choose? This one? We can't choose this one because you have a negative sign here. The value of cosine of pi over 6 without anything else is actually positive, root 3 over 2. So how do we choose the angle so we get a negative number here? Well, we can't go to the negative side because that's not allowed. That's not an allowed value for the range here. What is the range? It's from here from 0 to pi. Okay, remember the graph looks like this for the inverse cosine function. 0 to pi is up here. Okay, so we can't choose that, but we can go, here's 0 to 2 pi right here, or 0 to pi right here. So any of those angles will work, and the one which gives you negative can only be this one. What is that? It's pi minus pi over 6. So that's 5 pi over 6. Okay, that's the answer to the problem. And then part D. Part D is, what's the inverse tan of 1? Okay, so remember the inverse tangent function looks like this. It goes between, the range is all the values not including minus pi over 2 to plus pi over 2. So these two asymptotes, one for the values of x which go off to minus infinity, the other for the values of x which go to plus infinity. Okay, so tan of 1 is going to be, tan inverse of 1 is going to be up here somewhere. And you remember, what's the value of x so that tan x equals 1? And that's, if you remember the special values, it's pi over 4. So this is the answer. There's no other possible x in this domain, which will give you the same value of y, namely 1. Sorry, value of y is pi over 4. Value of x is 1. So there's no other, how are we going to say this? You start with the value of x, which is 1, and, sorry. You start with, well, this is mixed up here. This should be y. And then you're solving this equation. You get y equals pi over 4, okay? So the value, in terms of this graph then, I've chosen the value of the output to be y. So I solve the equation tan y equals 1. So there's no other value for y that gives us the tangent equal to 1, except this value, which is pi over 4. Okay. All right. Now here in the past, I was using x, but it's the same idea. It's just when I draw a graph and I want to choose a y-axis like this, then you see why it's better to choose a y there. Okay, but the same principle holds. If you replace all those values of x by y, then you can show it on a graph as well. Okay, let's try it number 2. We're in section 8 point something here, 8.3 now. Try it number 2 is find these inverse trigonometric functions. So sine inverse of minus 1 is, okay, so this is right at the edge of the domain of the inverse sine function, which looks like this. Remember? So minus 1 to 1. So it's right at this edge. So if you picture that, then it's easy to get the value. Should be minus pi over 2. The output values are angles. Input values are ratios, or real numbers. And if you just check that, take the sign of minus pi over 2, indeed that gives you minus 1. And it's in the correct domain here for inverse sine. Or the correct range, sorry, for inverse sine. Okay, next one, cosine minus 1, cosine inverse of minus 1. Here, drawing a quick graph, remember it looks like this. Minus 1 is over here. The largest possible value is pi, so this is pi. Okay. This goes from 1 to minus 1. The inverse tan now of minus 1. Okay, well, this gives us a clue. the tan function is an odd function, so it has a nice symmetry for its domain and range. And the same is true for the sine function. But because a cosine is not an odd function, it doesn't have that nice symmetry. So that's kind of the, so to speak, it's a different kind of function. It's a little, sort of the odd one out. That's the expression for. Even though the other ones are actually the odd one, and that's the even, or it's not an even function. The cosine is an even function, but not the inverse cosine. The sine is an odd function, and so is its inverse. Likewise for the tan function, it's odd. The tan function is odd, looking like this. Likewise, so is, oops, it's got a non-zero slope here. And likewise, the inverse tan is odd. So they're all odd except this one. That makes that one. Sorry, we call it the odd one out. But that's bad here. This is confusing. It's not odd at all. It's the only non-odd one. Okay, so tan inverse of -1 is just minus pi over 4. So maybe you just saw that right away. You didn't need all that explanation. So yes, that's correct. So you just, instead of going over to along this function here to where we did before, we went to 1 and we got pi over 4 here. You go to -1. It's just a reflection of that point through the origin. So that's minus pi over 4. And finally, cosine inverse of 1/2. That's the value, okay, the angle whose cosine is equal to 1/2. And thinking about that for a sec, you could write it down as well. Look at a unit circle, or you could try to draw the graph. It's not so clear if you draw the graph of this, actually. 1/2 will be here, so you could tell though it's going to be a positive value, but it's not totally clear that should be pi over 3, but it is. Okay, if you just remember the cosine of pi over 3 is equal to 1/2, and that this is basically just the same thing as that. Okay, let's do ones which require the use of a calculator. So if you use the calculator, then you have to shift, and then usually it's a shift and then the inverse trig function, right? Same key as the original function, but you need to use a shift key before that. So let me show it to you. So in this case, it's you have the shift function up here, shift button. Then you go, shift sine. Oh, let's turn it on. Shift sine. There you see the sine. And let's do it. Let's just write it in right away. See what we get. 0.97 equals. So you get 1.325. Etc., which is radians. Okay, so this, remember the input is a real number, the output of a inverse trig function is an angle in radians. Okay, the angle, it could be something greater than 1. What if we try this? Okay, let's try it. What do you think will happen here? sine of 1.5. Oops. Try that again. Shift sine okay, so here's the shift inverse sine of what I put in 1.5, and I go equals math error. Okay, why is that? It's because this number is not in the required domain. 1.5 is outside of the required interval, which is -1 to 1. So the number you put in here has to be less than 1 in absolute value in order to get any value at all. Okay, so it looks like this. For the inverse sine. What about for the cosine? Same thing. Inverse cosine will give you okay equals math error again. All right. So if you make it too large out of that range from -1 to 1, then it's not defined. What about for the tan? Okay, well, I'll have to continue this lecture some other time because somebody's at the door. So if you'll excuse me, I'll just log off here for a sec.
Hello.